In this video, we're going to continue drawing Lewis structures. So we're going to practice drawing Lewis structures, which have 3 elements or more. We're going to work on some compounds. So let's work on our first example. Let's draw a Lewis structure for carbon dioxide. So the first step is to count up the total valence electrons. So carbon, we're going to take a look at carbon over here. So it has 1, 2, 3, 4 valence electrons. Each oxygen has 6. 1, 2, 3, 4, 5, 6. So 2 in the 2 S's and 4 in the 2 P's for a total of 6. And then we have 2 oxygens, so we're going to multiply that by 2. So our total valence electrons is 12 plus 4, 16 valence electrons. So that's how many electrons we have available to us. Now we're going to put the least electronegative element in the center, which in this case is carbon, and we'll talk about trends in electronegativity a little bit later. So carbon's going to go in the center, oxygen on either side. So if you have your notes in front of you, your chapter 8-9 handout with the rules, guidelines for Lewis structures, you want to first connect these. So 2, 4, and then we can go up to 16. So first we connect these, then we put the other electrons that are left on the outer atoms. So 2, 4, 6, 8, 10, 12, 14, 16. Then we want to check. So now we've used up our 16 valence electrons, and now we want to check and make sure everyone's following the octet rule. So here you can see this oxygen has 2, 4, 6, 8. This one has 2, 4, 6, 8. But the carbon only has access to 2, 4 electrons. So we're going to go ahead and move some in so that carbon has access to the full octet. So 2, 4, 6, 8, 10, 12, 14, 16. So now we have the total number of 16 valence electrons. And then we're going to check for our octets. So oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And this carbon has 2, 4, 6, 8. So remember, they're sharing those. So our valid Lewis structure for carbon dioxide looks like this. Okay, let's move on to another example. So the first thing we want to do is draw up the total number of valence electrons. Each hydrogen has just 1 valence electron, so that 1s1. And we have 2 hydrogens for a total of 2 valence electrons. Carbon, 4, and oxygen, 6. So 2 plus 4 is 6, plus 6 is 12. All right, so we have 12 total valence electrons. So we're going to put the carbon in the middle. And typically, if you have one of these, I will let you know which element goes in the middle, since you don't have a lot of practice with it at this point. But carbon is an excellent building block. All of organic chemistry is based on carbon being a building block. So often carbon is going to be in the middle. All right, next we're going to distribute the other ones around it. So I'm going to put a hydrogen here, and an oxygen here. So then if you look to your guidelines, you want to single bond them first, then distribute the electrons around. Okay, so are we going to put more electrons on the hydrogen? No, because hydrogen follows the duet rule and it already has 2 electrons around it, so we cannot put any more electrons around hydrogen. So we're going to put them around the oxygen first. So 2, 4, 6, 8, 10, 12. So now we've used up our 12 valence electrons. Now we want to check and see if it's right. So this hydrogen has 2, this hydrogen has 2, this oxygen has 8, 2, 4, 6, 8, and this carbon has 2, 4, 6. So 6, not good. So we're going to take some oxygen or some electrons and move them in to make a double bond. So now each hydrogen is following the duet rule. Oxygen now has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. So this is a happy Lewis structure. So at this point, hopefully you're understanding how to draw Lewis structures. And I just want you to practice these a bunch. Like all the skills that we've learned, you're going to get better at it the more you practice. So we're going to keep drawing Lewis structures, but now we are going to move on to drawing Lewis structures for polyatomic ions. All right, so let's take an example of a polyatomic ion that we're already familiar with. Hydroxide. So remember, these are just those polyatomic ions that we've been working with since we started naming ionic compounds, found in that little square on the bottom of your periodic table. So now we're going to count up our total valence electrons. Oxygen, remember, has 6. Each hydrogen has 1. But now we need to take into account the fact that this is a -1. So if it's -1, that means it has 1 extra electron. So this sign here tells us that it has 1 extra electron. So 6, 7, 8. So now we're going to go through and draw it just like we've been doing it. So we put our O and our H. Then we bond it once. And now we're not going to put any more electrons around the hydrogen because it already has 2, so it's maxed out. We can't put any more electrons around the hydrogen. So 2, 4, 6, 8. So those are how many valence electrons we had to work with, 8. So we're good. Oxygen is following the octet rule, and hydrogen is following its duet rule. Now, the only other thing that we need to do for a polyatomic ion, we put it in these little square brackets and write the charge. So that's how we do it for polyatomic ions. So you still need to put these square brackets and indicate the charge. So let's practice another one. We're going to do hypochlorite. All right, so we have chlorine, an oxygen, and a -1 charge. So chlorine, let's go to our periodic table, and we'll see that chlorine is right here. 1, 2, 3, 4, 5, 6, 7. So the halogen family is always going to have 7 valence electrons. Oxygen, we've used a bunch already. We know it's 6. And our -1 charge is 1 extra electron. 7 plus 6 is 13, plus 1 is 14. So we have 14 total valence electrons. So now we're going to go ahead, put our chlorine, our oxygen, then we're going to put a single bond, then we're going to distribute the other electrons and see how it works out. So that's 2 electrons already. 4, 6, 8, 10, 12, and 14. Then we check to see if everybody's following the octet rule. Chlorine here has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Everybody's happy. Last step for the polyatomic ion is the square brackets and the charge. So this is our valid Lewis structure for hypochlorite. All right, so now you know how to draw Lewis structures for compounds and for polyatomic ions. And of course, anytime I tell you any rules, there are exceptions to rules. So we're going to go ahead and take a look at some of those exceptions to the octet rule. Okay, so one example is nitric oxide. NO. So if we try to draw a Lewis structure for this one, let's take a look at nitrogen, and we'll find nitrogen right here and see that it's 1, 2, 3, 4, 5 valence electrons. Oxygen has 6. So that's a total of 11 valence electrons. So you can probably already guess, since we have an odd number of electrons, we're not going to be able to get a pretty Lewis structure where everybody's following the octet rule. So in this case, you just kind of do the best that you can. And we're going to talk about formal charge in a little bit in the next section, but for now, because there is a reason why we're going to give oxygen the octet and not nitrogen, and that's because it's more electronegative. And we're going to get into formal charge later and explain how you choose which one is the best Lewis structure. But for now, I'm just going to show you that it looks like this. So oxygen here is following the octet rule, but you can see nitrogen just has 2, 4, 6, 7 electrons. All right, so this is called nitric oxide. This is produced in vivo by Viagra, for instance, to increase blood flow. And this is also used in some heart medications, I believe, nitric oxide. So when you have just one little electron here, this is called a free radical. So a free radical is anytime you have an odd number of valence electrons. And you guys have probably heard about free radicals. A lot of foods advertise, like blueberries and acai berries are supposed to be good for free radicals. All right, let's look at some more exceptions to the rules. So as I told you, hydrogen only forms a duet, but even some of these little guys here, they don't have enough protons to support having 8 electrons around them. So some of them will have fewer than 8 electrons, and that's how they're comfortable. Boron, for example, often forms compounds with only 6 electrons around it. All right, so BF3, you can see here, the fluorines will have the octet, but boron only has 6 electrons around it. Another example with boron is if you bond it with 3 hydrogens. So the hydrogens are still following the octet rule, but boron only has 6 electrons around it. And that's pretty common for boron. The other exceptions you can have to the octet rule is that some elements will form an expanded octet. So expanded octet meaning that it will have more than 8 electrons around it. So one element that does that is xenon. And I know I've told you that xenon is a noble gas and that it doesn't really bond with other things. Turns out that's not entirely true. So xenon has a really big electron cloud, which is one reason that they think that this can happen sometimes. Just that those bonding electrons are so far away from the nucleus of xenon because it has such a gigantic electron cloud. Phosphorus can also form an expanded octet. All right, so you can see that xenon here has 2, 4, 6, 8, 10 electrons around it, and this phosphorus has 2, 4, 6, 8, 10. So scientists have some different theories about why this can happen. It could be because they have access to those empty d orbitals, or maybe just because they're so big. So on the periodic table, you'll see that phosphorus is in the 3, energy level 3. So then it does have access to those 3d orbitals. So anything that's up here in the 2 row will not form an expanded octet. But when you get down here into, say, phosphorus or sulfur, you can get those expanded octets. And then as we just saw with xenon. So there's still some debate about why and how that happens exactly. All right, so those are some exceptions to the octet rule. So boron, for example, can have just 6 electrons around it, and then you can have these expanded octets for elements of row 3 and below. All right, so I think the last thing we're going to look at for Lewis structures are what are called resonance structures. So sometimes a compound, you can write more than one valid Lewis structure. So then you have resonance structures, where the true geometry is an intermediary between the structures. All right, so let me show you an example of what I mean by that. So let's take a look at sulfur dioxide. So I'm not going to go through all the steps of writing out the Lewis structures with you here, but you can go ahead and use that same count up the valence structures, valence electrons, and then distribute it like you have been. So this is one valid Lewis structure for sulfur dioxide. You can see that everybody's following the octet rule, but there's no reason that this oxygen would have a double bond rather than this one over here. So it is equally valid to put the double bond between the other sulfur and oxygen. Then we draw a little arrow between it to say that this is a resonance structure. So the entire valid Lewis structure is this thing. So if I asked you to write the Lewis structure for sulfur dioxide, you would actually write this entire thing, both of these Lewis structures with the arrow in between. So it turns out that in reality, it's more like a 1.5 bond. So this true compound, it doesn't have one long bond and one short bond. It's kind of like a 1.5 bond. So you might see it written something like this. You might come across something like that on the internet, but I don't want you to write that. This is the one that I would want. I would want that first one written for the resonance structures. So the bond order for this one is 1.5. So it's not really a single bond. It's not a double bond. It's kind of like a 1.5 bond. So we do have some situations like that, and these are called resonance structures. So let's take a look at another example of these. All right, so this is a polyatomic ion. So let's count up the valence electrons. Nitrogen has 5 electrons and each oxygen has 6, and we have 2 of them. And then that -1 is 1 extra electron. So 12 plus 5 plus 1 is 18. So I'm just going to scroll up. All right, so let's say we had 2, 4, 6, 8, 10, 12, 14, 16, 18. So we used up our 18 valence electrons. But as you can see, if you look at this, nitrogen does not have that complete octet. So we're going to take one of these and move them in. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So now we have our 18 valence electrons. Each element is following the octet rule. But as you can see, just like the sulfur dioxide, there's no reason that we would have a double bond for one of these and not the other, because they're totally equivalent. So then what we want to do is just draw another one of these guys with the double bond on the other side. And then we put our little arrow in between. And this one, since it is that polyatomic ion, remember we have to have the square brackets and the charge. So this entire thing, if I asked you to draw a Lewis structure for NO2-, you would draw all of this. So that's our valid Lewis structure for that. All right, so now you know how to draw Lewis structures of elements, compounds. You know a little bit about the exceptions to the rules, and you know how to draw resonance structures. So now I'm gonna put up a slide, and it's also the example on your handout. So I want you to go ahead and try to work these out on your own. Okay, so you can grab your handout or just keep this up. These are some different ones for you to work out. So practice drawing Lewis structures. See if you can draw a Lewis structure for each one of these. And the hint for this last one is that you are going to need some resonance structures. So if you do want to work on that right now, go ahead and pause the video because I am about to show the answers. So pause the video now and work on these problems. Practice drawing these on your own. Okay, so let's take a look at the first one. All right, so we have HF here. Hopefully this is what you got for the Lewis structure. So here we're following the duet rule. Here we're following the octet rule. So hydrogen has 1 valence electron, fluorine has 7. So this is the Lewis structure for hydrofluoric acid. Then let's take a look at CF4. Hopefully you got something like this. Carbon in the middle, the fluorine's attached. Everybody following the octet rule. Now let's look at NO+. So nitrogen had those 5 valence electrons, oxygen had 6, and then since this is a plus, you're actually going to remove 1. So 5 plus 6 is 11, minus 1 is 10. So you should have gotten 10 valence electrons for this one. 2, 4, 6, 8, 10. So then both of these are following the octet rule. Put it in square brackets and the plus sign. Now for this last one, you had to come up with different resonance structures, and there can be more than 2. So here we have it. You counted them all up. Carbon has 4 valence electrons. Each oxygen has 6. And then you're going to add 2 more electrons for the -2. So when you draw your Lewis structure, you'll find that you need 1 double bond, but there's no reason that this one should be double bonded rather than this one or this one. So then you're going to go ahead and draw your little arrows and put the double bond somewhere else, and then draw your little arrows and put the double bond somewhere else. And these could be written in any order. And since it's a polyatomic anion, you have to have these square brackets with the charge. All right, so hopefully you got all these answers right, and if you didn't, that's okay. Just go ahead and keep practicing drawing Lewis structures. I want you to get really good at these, so just practice as much as you can. And that'll be the end of this video. I'll see you next time.